Welcome to qnawire.
Please take a look at this diagram here. So to find the moment of inertia, we will use parallel axis theorem. So IA will be equal to moment of inertia of the body plus moment of inertia of these arms. Now moment of inertia of the body, since the body is a cylinder, so we should have half times mass of the body times square of the radius of the body. And moment of inertia of the arms, so basically we have two arms and moment of inertia of both should be equal because they have the same length from the cylinder. So we have twice of moment of inertia of each arm, which will be equal to 1 over 12 moment of inertia of arm times length of the arm, square of the length of the arm, which is L here. So this term is the moment of inertia about this point, about the end point of the arm. Now we have to take the moment of inertia of this factor from this point to the center. So moment of inertia of this term into account. So that will be equal to mass times the total length, which is radius of the body or of the cylinder, plus half of length of the arm square. So yeah, so I forgot to mention A here. Yeah, now we are given that mass of the body or mass of the cylinder is 60 kg, RB is 0.12 meters, mass of each of these arms are 5 kg, LA, which is the length of the arm, is 0.6 meters. And plugging these values over here and solving them, we get IA to be equal to 2.496 kg meter square. So let me repeat this part once again. I think this might be a little confusing to grasp. So this is the moment of inertia of, I think I said the end point, actually the inertia of the through the middle of the rod, and so from here to here, this is the middle of the rod, and by parallel axis theorem, since we want the moment of inertia about this axis, we have to consider this extra moment of inertia. So we have to consider this as a point mass and take the moment of inertia of this point around here. And this is what that term is. So we multiply the mass of the arm times the radius, basically this length, which is RB plus half of LA. Now another method, the same parallel axis theorem, but an alternate way of using this will be what I was referring to initially. So take the moment of inertia about this point for the arm. So that is 1 over 3 ma LA square. Then by parallel axis theorem, you have to multiply, you have to take the moment of inertia of this gap. So that will be ma times RB square. And if you solve this equation and simplify this part, you will ultimately arrive at this part itself. So these two expressions are basically same, and using either of them will yield you the same result for moment of inertia. Now moving on to part B. So this was part A. Moving on to part B, now the arms can be treated like particles because so we have the cylinder, radius of the cylinder which is RB, mass of the cylinder is M, and now the arms are like this. Now since these arms are at the same distance from the axis of rotation as this edge of the cylinder, so we can treat the arms like particles. So IB will be, that is moment of inertia in part B, will be equal to, so basically the same thing, moment of inertia of the body plus moment of inertia of the arms. So this is the total moment of inertia. Then we use parallel axis theorem for moment of inertia of the arms about this axis. So moment of inertia of the body is basically half mb/rb squared because the body is a cylinder, has a cylindrical shape, and I of arms will be, so as before, similar to this case, we have two arms of equal mass and at the equal distance from the axis passing through the middle, passing through the axis of the cylinder. So we multiply 2 with the moment of inertia of each arm, and that will be equal to mass times RB square. Now this is because each of these mass is situated at a constant distance from R, and each of these segments of mass is also at a constant distance. Therefore, there is no integration over mass involved. We can just take the total mass m for the mass of each arm and multiply it by the radius, square of the radius of the mass from the axis of the cylinder. So doing that, now we can substitute the values for this over here, and we get the moment of inertia in this part to be 0.58 kg times meter square. I think I said kg per meter square over here. I don't remember, but yeah, this is kg times meter square. Since the angular momentum is conserved through the change in posture because there are no external forces involved, so angular momentum is conserved. Therefore, we can write this to be IA omega A, which is angular momentum for part A, to be equal to IB omega E, which is angular momentum for part B after there is a change in the posture, after the arms are now inclined or situated in a different kind of way with respect to the cylinder. Now let's use omega to be equal to 2 pi over time period. So for omega A, we have 2 pi over time period of in part A to be equal to IB times 2 pi over time period in part B. This gives TB to be equal to IB over IA times TA. Now TA is given to be 1.5 seconds. So we plug this value over here, including the values of IA and IB that we found in the previous parts, and solving them we get TB to be equal to 0.3462 seconds. Now, moving on to the fourth part. So, we know that the change in kinetic energy is basically the final kinetic energy where the arms are horizontal. So, basically, this, sorry, this times, so let me just write Kf to be Ka minus Kb. So here the arms are at sides, and we know that kinetic energy for rotational motion is half I omega square. So for initial case we have Ia omega A square, and for the final case we have half Ib omega B square. Now we already know what to use for omega A. We basically use omega A to be 2 pi over Ta, and omega B we use 2 pi over Tb, and we already know the values of Ta, Tb, Ia, and Ia and Ib. So we use those four values, plug them into this equation, and find the change in kinetic energy to be equal to negative 73 joules. Now, because of the change because of the decrease in the kinetic energy, it is easier to lift the arms when rotating. There is no corresponding change in kinetic energy if the person is at rest. However, in the rotating system, the arms tend to move away from the center of rotation, which is this axis. Now, another way to express this is that it takes work to bring the arms into the sides when rotating. So, if you are going from A to B, we need work to be done to go from posture A to posture B. And this comes from the relation where work is basically change in kinetic energy. Now, if work is positive, work is done by the system, and the system here is this whole cylinder plus arm system. And if work is negative, work needs to be done on the system. So therefore, to change from A to B, we need work to be done on the arms in order to bring the arms into the sides when rotating.